Hello, everybody. Welcome back to More on Math. Today, we're going to talk about Chapter 5, Section 1, Inverse Functions. The objectives we're going to do here are we're going to look at how to determine if a function is one-to-one from now on. When instead of writing out one-to-one, I'm just going to put this as an abbreviation. We're going to determine how a function, if the function is at one-to-one. If it is, then we're going to find its inverse. The inverse is, the regular function is f of x. The inverse of a function is noted by that -1 on top. That's how you know it's an inverse function. That separates the two. And then if we're using y's, it'll be like that. The next thing we're going to talk about is we're going to simplify expressions. Right. In chapter 2, section 3, we covered the first part of this. We talked about compound function, composite functions. We're going to look at simplify expressions like this. So we're going to look at simplifying compound functions. So a review of chapter 2, section 3. If I have two functions, f of x, let's say it's 2x plus 3, and g of x is 5x minus 5. Remember the old Fogg-Goff discussion? If I had f of g, this is read f of g of x. So when you compress it, because as you read it, it goes f of g of x. So it's g of x on the inside. That is in place of x of the f function. So what that means is this equation goes inside the parentheses. That's what g of x is. Since this is whatever's inside the parentheses is what x is. So inside this equation, in place of x, we put 5x minus 5 and plus 3. That's the last part of the equation. So it's 2x plus 3. Get rid of the parentheses, distribute. 10x minus 10 plus 3. Combine like terms. Negative 10 plus 3, 10 is bigger, so it's negative. 10 minus 3 is 7. So there's the function f of g. And now we've got to do it the other way. We also talked about the Goff. So basically what this means is in this first one, whatever's the second letter, that equation goes in place of the x in the first equation. So whatever's second goes in place of the x of the first equation. So the second equation goes in place of x. So this 2x plus 3 goes in place of x in the g of x. So what I have here, I have 2x plus 3, that's the f of x function. And that equals 5, 2x plus 3 minus 5. Distribute 10x plus 15 minus 5. 15 minus 5 is 10, positive 10. And there's that function. So that's what we did in chapter 2, section 3, which we're going to need those concepts in this chapter. All right. So let's look. What do we mean when we say inverse function? What do we mean? An inverse function is the opposite of a regular function, of the original function. So if inverse function, the way we find it, so we had 2x plus 3. So how do we find the inverse function? First step, change f of x to y. It makes it much easier, even though we know that f of x equals y. Second step, switch x and y. So I switch x and y. Now solve for y. And whatever you get there, that y is actually your inverse. So we subtract 3 from both sides. So x minus 3 equals 2y. Divide by 2. So this is the y, since that's what I'm solving for. It's the inverse. There's my inverse function. There was my original function. And in a little bit, I'm going to show you how to test to see if those really inverses. What if I gave you a set of numbers? These are all points. Remember, this is x comma y. The inverse of a function. First off, we know it's a function because all of the x values are different. That's the first condition, remember, it's the vertical line test. It has to be a function first. So to find the inverse, remember our first step, switch x and y for each point. So there's the inverse function. So there's the original function. Its inverse is, remember, just switch x and y's. All right. We'll talk about the conditions in a little bit. Oh, here's an interesting note. the graph of an inverse function is a reflection of the original function across the line y equals x. The line y equals x is the diagonal line through the origin. So when we graph inverse functions, what we actually flip it. So if you want to know the actual graph, fold your paper diagonally like this and press down hard on the graph, and you'll make the inverse of the graph. For example, if this was 1, 2, that can't be, because this has to be on the y line. So that's 2, 2, 3, 3, 4, 4. It works both ways. The reason it does that, because if I switch x and y, I still have 2, 2 on that line. We're going to look at other lines later on. Inverse and one-to-one functions. Remember, what does one-to-one mean? That means for every x, it maps to only one y value. They can point to the same one. So this is one-to-one. So one of these to one of those. Not one-to-one. Because one of the x's do not make that. Remember I said we had that list. As long as all of the x's are different, you have a one-to-one function. That's the reason why. If all the x's are different, it doesn't matter what the y's are. So it's define one-to-one. One-to-one function. A function is one-to-one if different inputs, those are the x values, do not equal different outputs. So what that means is this. A function with x has to point to, well, it cannot point to a different function, because it has to have different x's, remember? So to test if a function is one-to-one, we know that this has to be true. If f of A equals f of B, then A has to equal B. Very important, because remember, equals, you have to go both directions. It's very important, though. So to test the function, f of A equals f of B. We'll look at that in a second. So here are the properties. So I want to have a little bit of space. Those properties of one-to-one functions. Okay, so if f of x is one-to-one, then f, the inverse of f, is a function. Remember, what is a function? A function has to pass the vertical line test. It cannot have, a vertical line cannot cross the graph more than once. The domain of a one-to-one function is negative infinity to positive infinity. All real numbers. The range domain of a function, a one-to-one function, is the domain of a one-to-one function is all real numbers. A function that is increasing or decreasing on the domain is one-to-one. Remember, if it's increasing, means that as x gets bigger, y gets bigger. That's increasing. Decreasing, as x gets bigger, y gets smaller. That's decreasing. But because of that, it still has to remain a function. So let's see how we actually test for it. Let's pretend we're given a function f of x equals 2x minus 3. Prove that it's one-to-one. So remember we said earlier, to be one-to-one, f of A has to equal f of B, and then at the end, A has to be, it has to be the same number. So we'll do the same thing here. F of A has to equal f of B. That's what that says. So here's our function. So we have 2a minus 3, 2b minus 3. But that's where we put some of the x. Let's solve for the letters. Add 3 to both sides. 2a equals 2b. Divide by 2. A equals B. And that's exactly what we're supposed to prove. So that means that function is 1 to 1. Okay, let's look at another example. Of a function that's not 1 to 1. To prove that it's 1 to 1, we have to prove this. So we have a squared equals b squared. To get rid of the square, we have to square root both sides. Whenever you square root something that's squared, you have to put a plus or minus on the other side. So the answer becomes plus or minus a equals plus or minus b, because those cancel. Not 1 to 1, because what this thing says is positive a equals plus or minus b. Negative a equals plus or minus b. Too many different combinations. It doesn't satisfy the condition a equals b. So that's not 1 to 1. Remember, we use the vertical line test to prove that a function is a function. Because if it crosses it more than one, if the vertical line crosses it more than once, it's not a function. So remember, we switch x and y, so we rotate it. Here, we use a horizontal line test. To prove, oh, my pen's dying. To prove that a function is 1 to 1. The horizontal line test says this. If a line crosses the graph more than once, it is not 1 to 1. If it's not 1 to 1, and its function, inverse function, I should say, and its inverse is not a function. And it's actually, its inverse is not a function. So the horizontal line test, it proves if it's 1 to 1. If a line crosses the graph more than once, then it's not 1 to 1. And its inverse is not a function. Here's some examples. We have a diagonal line. We have a parabola. The cube root function. And the cubic function. So a horizontal line test, it passes, this is 1 to 1. This one fails, not 1 to 1. This one, the horizontal line test, proves that it's 1 to 1. This one is not 1 to 1. All right, so to find the inverse, remember, switch X and Y, solve for Y. Of course, change f of X to a Y first. So for example, well, we did this one earlier. Change f of X to Y, change X and Y, solve for Y. Move the 3 over. It's by adding 3 to both sides and divide by 2. So Y equals X plus 3 over 2. And since it's a linear equation, it is 1-to-1, so it is a true function, or inverse function. Let's look at another one. F of X equals X cubed plus 2. Remember what this is a cubic function, so remember what the graph looks like. The cubic function looks like that. Raises up 2 spaces. So now the graph is this. This one here is just X cubed. The transformations. So first off, change that to Y. We see that it passes the horizontal line test. Switch X and Y. Solve for Y. Subtract 2. To get rid of the, we have Y cubed equals X minus 2. To get rid of the cube, we have to cube root both sides. So Y equals cube root of X minus 2. So remember, X cubed, or cube root of X is like that. That's cube root of X. Since the change is happening here, it shifts to the right 2 spaces. And it's still 1-to-1 because it passes all the horizontal line tests. All right, so this is how to find 1-to-1, the inverses, and prove how they're 1-to-1. Test 1-to-oneness. That's my one word. We use compositions. Basically, this is the reason. If a function f of X is 1-to-1, then its inverse is unique. There's only one equation for every inverse for everyone. If it doesn't, if it has more than 2, if it's 2 or more, it's not 1-to-1 because it's got more than that. So if that's true, then this also must be true. If we do a composite function, the answer should be X. And if we do it the other way, inverse of f, it should also equal x. If it's 1-to-1, if it's unique, then that should be the solution. It should, when we do the composite function, you should end up with x. Let's look at this example. F of x equals 5x plus 8. Find its inverse. So we have y equals 5x plus 8. Subtract 8 from both sides. Y minus 8 equals 5x. Oops, got to switch x and y first. That becomes x. That becomes y. X, y. And divide by 5. So the inverse of y equals x minus 8 over 5. So those are our two functions. Let's test it. In order to test it, we have to plug it into this compound function. Remember, it's whatever comes second goes inside the first. So this equation goes in place of x in this first equation. 5 x minus 8 over 5 plus 8. So 5 x is x over 8 plus 5 plus 8. Simplify. The 5's cancel. Before you multiply, always can reduce first. So we have x minus 8 plus 8. The 8's cancel. We have x. Check. That's the first one checked. Now we have to test the second one. Take the original function, put it in place of x in the second one. So we take this function, put it in place of x in the second. So that means we have 5x plus 8 minus 8 over 5. 5x plus 8 minus 8 over 5. 8 minus 8 cancel. 5x over 5 is the inverse. Let's take another one. F of x equals x squared minus 2. So that's y equals x squared minus 2. We have to find the inverse. So first step, we change that to that, switch x and y, and solve for y. So it's x plus 2 equals y squared. Square root both sides. We get y equals plus or minus x plus 2. It's not 1-to-1 because there's 2 of them. It's not unique. So we can make it 1-to-1 by restricting the domain. What does that mean? If our function looks like this, it fails the horizontal line test. The reason it fails the horizontal line test because negative x and positive x give you the same answer. And this is the domain is negative infinity, positive infinity. It's continuous. Restricting the domain. Instead of from negative infinity to positive infinity, let's get rid of half of it. Now it's 1-to-1. So the inverse exists. Our new domain goes from 0 to infinity. So that's how we can restrict the domain. All right, that's the end of section 1. Good luck, everybody.